Gazing up at the clear midnight sky, you are able to perceive thousands of shimmering stars using nothing but your naked eyes, provided you are positioned far away from the blinding illumination of modern urban centres. As a matter of fact, the vast canopy above contains a far greater abundance of stars that remain altogether too dim and faint for our unaided vision to detect. Every solitary star that you can spot with your eyes is an intrinsic component of our vast Milky Way galaxy, which serves as our magnificent celestial residence that has completely mesmerized human curiosity for countless generations. This glittering ribbon of suns, cosmic debris, interstellar gas, and mysterious dark matter stretching across the night sky continuously grabs our deep fascination. All of these diverse elemental components are firmly bound to one another by the invisible pull of gravity as we journey through the grand design of the cosmos. During this cosmic voyage, a highly fascinating puzzle begins to present itself to us. What does the Milky Way actually look like when viewed as a whole? What specific components combine to form its massive structure? And where exactly does our own small solar system reside within this sprawling stellar city? Professional stargazers and astronomers have found themselves deeply perplexed by these core inquiries for many hundreds of years, and uncovering concrete solutions to these puzzles was never an easy endeavour. Yet, underneath its radiant and sparkling aesthetic beauty lies a complex web of deep secrets that are desperately waiting to be solved. Come along with us on our journey today as we set out on an incredible and awe-inspiring exploration across the length of the Milky Way, shedding light on its hidden secrets, its magnificent wonders, and its breathtaking scale. It is highly likely that you possess a decent amount of familiarity with our immediate solar neighbourhood. If nothing else is known, you are probably already well aware of the fact that this neighbourhood encompasses a total of 8 distinct planets alongside our home world, the Earth. It also features our central star, the Sun, a variety of orbiting moons, and numerous alternative space objects such as wandering asteroids and the dwarf planet Pluto. Even so, an immense realm of discoveries exists far past the boundaries of our solar neighbourhood that you might not currently know about. Looking out from the surface of the Earth, human beings can observe roughly 6,000 individual stars without needing to look through any kind of magnifying telescope. Even though that sounds like an incredibly massive collection of stars to look at, it actually stands for an exceptionally minuscule fraction of the entire galactic population. In reality, for every single star that you are capable of seeing with your eyes, there are more than 20 million additional stars that you cannot see at all. The vast majority of these celestial bodies are either far too faint to notice, positioned much too far away in deep space, or completely hidden from our view by thick, enveloping clouds of interstellar dust particles. While our home Milky Way galaxy holds every single one of these countless stars inside its structure, there are also alternative, much more massive galaxies out there in the void, which includes our prominent cosmic neighbour, the Andromeda Galaxy. Every single galaxy in existence is a massive organised structure composed of diverse stellar remnants, an extensive interstellar medium, and complex independent star systems. Scientists who study the sky hold the belief that there are roughly 100 billion individual galaxies scattered throughout the wide cosmos, although they still lack absolute certainty regarding this figure. The vast, empty expanses of intergalactic space, which are filled only with an incredibly sparse, thin gas, serve as the giant buffers separating these massive islands of stars from one another. When we take into consideration the staggering scale of our independent solar system and contrast it with the reality that it represents just one single system among countless others in our galaxy, it becomes fully clear why the broader universe is widely considered to be boundless and infinite. This realization truly serves to offer a grounded perspective regarding just how incredibly minuscule both our home planet Earth and the entire human race really are when placed against the grand fabric of the cosmos. Through the practical utilization of highly advanced radio and high-energy X-ray telescopes, modern researchers have managed to assemble a wealth of detailed data over the course of the previous 100 years regarding the actual material makeup of the interstellar medium. They have successfully demonstrated that this vast space is composed of an extraordinarily scattered mix of electrically charged hydrogen atoms, microscopic dust grains, and high-energy cosmic rays that are widely dispersed throughout massive, dense clouds of interstellar gas. These thick gas clouds are generally recognized by scientists as the celestial nurseries where brand new stars are continuously brought to life. However, because of the overwhelming presence of our central sun, its collection of 8 orbiting planets, and a very distant, sprawling ring of frozen debris commonly identified as the Kuiper Belt, the exact characteristics of the space sitting right outside our immediate solar system have stayed largely shrouded in mystery. This far-off structure, known as the Kuiper Belt, is positioned at a distance ranging between 30 and 50 astronomical units away from our central sun. For context, a single astronomical unit represents the standard distance separating the Earth from the Sun. A massive protective magnetic envelope known as the heliosphere, which is continuously generated by the outward flow of the solar wind, completely blankets all of these internal components. This cosmic envelope pushes back against the surrounding interstellar medium like a protective, unseeable shield, successfully obstructing the entry of the most destructive cosmic rays and other hazardous space materials as our sun and its accompanying family of planets race together through the galaxy at extreme speeds. If it were not for the constant protection of this heliosphere, the development of living organisms on Earth would undoubtedly have taken a completely different path, and it is entirely possible that life would never have emerged at all. The specific boundary zone where the protective magnetic bubble produced by our sun finally hits its limit and begins to diminish is formally recognized as the border of interstellar space. The heliosphere, which behaves as a giant magnetic shield, is entirely packed with active plasma, which is simply ionized gas. The constant solar wind, which drags magnetic field lines outward and away from the sun, constantly pumps material into the interior of the heliosphere along with its independent magnetic fields and fast-moving charged particles. At the same time, the plasma resting out in the interstellar medium applies a continuous inward force against the outer boundary of the heliosphere, which creates an incredibly sophisticated and ever-shifting structural interaction at that boundary zone. As the outgoing solar wind collides directly with the incoming pressures of interstellar space, it experiences a dramatic drop in strength and rapidly drops its velocity down to roughly 62 miles per hour. Prior to reaching this barrier, the solar wind was racing along at tremendous velocities ranging between 370 and 430 miles per hour. The exact transition zone where this sudden slowing occurs is called the termination shock. Following this termination shock, we find the heliosheath, which is the specific region within the greater heliosphere where the solar wind continues to lose its forward speed. Meanwhile, the absolute outer limit of this entire solar bubble is known as the heliopause. The outward rushing solar wind completely grinds to a halt at this heliopause, officially giving way to the true realm of interstellar space, with this boundary sitting at a distance of roughly 11 billion miles, or approximately 18 billion kilometers, away from our central sun. 5, 4, 3, 2, 1. We have ignition, and we have a liftoff. Since the historical dawn of human space exploration, a mere 2 robotic space probes have ever managed to successfully journey deep enough to cross into true interstellar space, which is the completely open territory existing entirely outside our solar system's boundary. Following its initial launch back in the year 1977, Voyager 1, which stands as the pioneering spacecraft of this mission, required a journey lasting more than 3 full decades just to finally arrive at the heliopause. This is the precise cosmic boundary line that modern researchers accept as the true starting point of the interstellar deep. It stood as an absolutely monumental triumph of human engineering, successfully transmitting priceless scientific information back to Earth through a cosmic medium that remains completely unaltered by the influence of our sun. Once we fully depart from the outer limits of our solar neighbourhood, our journey will eventually take us to Alpha Centauri, which is a fascinating triple star system that holds the title of being the absolute closest star system to our home planet Earth. It is situated at a distance of roughly 4.37 light-years away from us, resting inside the boundaries of the southern constellation Centaurus. This system is composed of 3 distinct individual stars, which are officially named Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. The primary components are Alpha Centauri AB, which form a binary star pair consisting of Alpha Centauri A and B. Both of these are highly reminiscent of our own Sun, with astronomers classifying them as stellar classes G and K, respectively. When viewed together from Earth with the naked eye, these 2 primary stars exhibit a combined apparent magnitude of 0.27, which causes them to merge together and look like a singular, brilliant point of light. In the entire night sky, only the prominent stars Sirius and Canopus possess a greater level of brightness than this system, which makes it the single most radiant star structure in the Centaurus constellation and the 3rd brightest stellar object visible in our night sky. When we look at Alpha Centauri B individually, it is noticeably smaller and significantly cooler than its companion Alpha Centauri A, possessing roughly 0.9 times the total mass of our Sun and less than 0.5 times the Sun's total luminosity. On the other side of the pair, Alpha Centauri A boasts roughly 1.5 times the total brightness and 1.1 times the overall mass of our Sun. These 2 primary stars require an orbital period of about 79 years to complete a single revolution around their common gravitational centre of mass. Because of the highly elongated and eccentric nature of their elliptical pathway, the physical distance separating star A from star B shifts dramatically over time, moving from a maximum separation of 35.6 astronomical units, which is roughly equivalent to the immense distance separating Pluto from the Sun, down to a minimum proximity of just 11.2 astronomical units, which is roughly comparable to the distance between Saturn and the Sun. Shifting our focus to the 3rd member of the Alpha Centauri system, we encounter Proxima Centauri, which is the specific star that sits closest of all to our home Sun. It is located at a distance of approximately 4.2 light-years away from the Earth. A Scottish astronomer named Robert Innes was the first person to successfully make the discovery of this nearby neighbour back in the year 1915. Proxima Centauri is categorised by scientists as a red dwarf star, which represents the single most widespread and common type of star found throughout the universe. In terms of physical scale, it is roughly 7 times smaller than our Sun, and its outer surface temperature is just a little bit over half as hot, measuring in at approximately 3,100 Kelvin. By comparison, the surface of our own Sun burns at a much higher temperature of 5,772 Kelvin. To help put its diminutive size into perspective, this small celestial body is only about 50% larger in physical dimensions than the gas giant planet Jupiter. Because red dwarf stars are capable of burning through their internal hydrogen fuel supplies in an exceptionally slow and highly efficient manner, they are blessed with extraordinarily long lifespans. In fact, Proxima Centauri is confidently projected by astronomers to remain stable in its current life cycle stage for a staggering duration of more than 4 trillion years. Even though the broader Alpha Centauri star system can be easily spotted inside the Centaurus constellation, the individual star Proxima Centauri is typically impossible to view with the naked human eye. Proxima Centauri travels on a massive outer orbit around the primary binary pair of the system, Alpha Centauri A and B. Because this orbit is so vast, Proxima Centauri requires an incredible 550,000 Earth years just to finish one single revolution around its companion stars. Showing an apparent visual magnitude of 11, Proxima Centauri is easily the faintest and dimmest of the 3 stars that make up the system. This dwarf star radiates energy at a significantly slower pace than our Sun, possessing a total luminosity that amounts to a mere 0.17% of our Sun's total light output. In spite of this dimness, Proxima Centauri is formally classified by astronomers as an active flare star, meaning it is highly susceptible to undergoing sudden, violent solar eruptions. This instability means its overall brightness can fluctuate wildly by more than a full magnitude category in a span of just a few minutes. These intense eruptions, which break out across the star multiple times every single day, carry the potential to become powerful enough to briefly boost Proxima Centauri's brightness to the point where it could actually be seen by an unaided human observer on Earth. The single most violent solar flare ever recorded by scientists anywhere inside the Milky Way galaxy was unleashed by Proxima Centauri back in the year 2019. During this extreme event, the star flashed an astonishing 14,000 times brighter than its normal baseline state when measured in ultraviolet wavelengths of light. Even though Proxima Centauri will continue to exist for a vastly longer period of time than our own Sun, it is destined to eventually suffer a highly comparable cosmic fate. When its internal hydrogen supply ultimately runs completely dry, Proxima Centauri will finish its life as a cooling, faint white dwarf star. It simply lacks the necessary physical mass required to trigger a more violent end, such as collapsing into a dense neutron star or a black hole. As of the year 2022, professional astronomers have successfully confirmed the presence of 3 distinct exoplanets orbiting around Proxima Centauri, which have been named Proxima b, Proxima c, and Proxima d. These 3 objects hold the record for being the absolute closest alien planets discovered anywhere outside our own solar system. Because red dwarf stars are naturally quite small and cool, their orbiting planets can circle at exceptionally close distances while still being officially categorized as resting inside the star's habitable zone. This term describes the specific range of orbital distance from a parent star where an orbiting planet's surface water, assuming any is present, could exist in a liquid state and therefore potentially foster the development of life. Proxima b was initially discovered by scientists back in the year 2016, with data indicating that the planet possesses roughly 17% more mass than our own Earth, making it highly likely to be a solid, rocky world. Even though Proxima b is positioned vastly closer to its host star than the Earth is to our Sun, it still sits comfortably within Proxima Centauri's habitable zone. It races around Proxima Centauri on a rapid orbit that takes just 11 Earth days to complete, maintaining an orbital distance of about 0.049 astronomical units. This means it is over 20 times closer to its star than the Earth is to the Sun. Because of this intense proximity to its parent star, Proxima b is highly likely to be tidally locked in place, much like our Moon is locked to the Earth, meaning one side of the planet permanently faces the star while the other side rests in eternal darkness. Given this situation, it remains entirely possible that liquid water could persist on the side facing away from the star, but its actual capacity to support living things stays completely unverified because of the intense radiation fields and violent stellar flares launched by its host star. Furthermore, any potential life forms on Proxima b would experience the gravitational pull of their parent star far more intensely than we experience the tidal forces of our Sun here on Earth. In our own home system, the Moon exerts a much greater tidal influence on our planet than the Sun does, simply because the Moon is located so much closer to us. Tides do not merely pull on surface bodies of water, they are also capable of shifting and pulling massive bodies of atmospheric air. Because of this, it is entirely possible that the gravitational tidal pull exerted on the atmosphere of Proxima b could be up to 500 times more powerful than the tidal pull experienced by Earth's own atmosphere. It appears highly probable that Proxima b is currently experiencing a level of gravitational distortion that sits right on the absolute upper limit of what a planet can safely endure without losing its solid planetary surface entirely. Despite these massive gravitational forces, the overall climate patterns and daily weather systems of Proxima stay mostly undisturbed by its incredibly powerful tidal shifts. Moving further outward from the star, situated just past the boundary of the habitable zone, at a distance of roughly 1.5 astronomical units from the red dwarf, we find the mini Neptune-class exoplanet known as Proxima Centauri c. This planet is roughly 7 times more massive than the Earth and requires a total of 1,900 Earth days to complete a single orbital revolution around its host star. Originally spotted by astronomers in the year 2019, this massive super-Earth or mini-Neptune planet appears to reflect and emit a level of light that is significantly more intense than scientists would expect for an object of that particular size. This anomaly indicates to researchers that the planet might be completely enveloped in thick dust clouds, or perhaps surrounded by a massive cosmic ring system. The calculated surface temperature for this planet is extraordinarily freezing, with astronomers estimating it to be somewhere close to 233 degrees Celsius. This extreme cold, combined with its substantial distance from its star and its massive size, makes it completely uninhabitable for life. The immense gravitational pull of Proxima Centauri originally caused its parent star's orbital velocity to undergo a slight wobble, which is what initially tipped off astronomers to the planet's existence back in 2019. Later on, in the year 2020, historical images captured by the Hubble Space Telescope all the way back in 1995 were carefully reanalyzed to fully confirm the existence of Proxima Centauri c. Because of this, it stands as one of the exceedingly rare exoplanets in astronomy that has been backed up by direct visual confirmation. A third independent planet was successfully located orbiting the star in the year 2022. This particular exoplanet, which has been designated as Proxima Centauri d, circles its parent star at a tight distance that equals a mere 3% of the distance separating the Earth from our Sun, and it holds a mass equal to roughly 25% of the Earth's mass. Proxima Centauri flies around its star at a blistering pace, finishing one full orbit every 5 Earth days. Because of its extreme proximity to its star, it ranks among the absolute lightest and least massive exoplanets that modern researchers have ever managed to observe. Adding to these discoveries, in the year 2021, a team of scientists picked up what could be the very first concrete evidence pointing to an exoplanet orbiting around Alpha Centauri A, which is also frequently referred to by its alternative name, Rigil Kentaurus. Located directly within that star's habitable zone, this candidate world has been temporarily named C1. Stargazers estimate that this planet C1 possesses an overall mass that falls somewhere between half the mass of Saturn and the mass of Neptune, and it circles Alpha Centauri A at an orbital distance of approximately 1.1 astronomical units. This candidate world was detected through the utilization of direct thermal imaging technology, showing an elongation of roughly 0.1 arcseconds. It displays a level of brightness that perfectly matches what one would expect from a giant planet. This appearance aligns with the predictable orbital movement of a planet travelling along a 70-degree orbit. The reality that candidate C1 is located right inside the habitable zone of Alpha Centauri A, combined with the possibility that it could be a mini-Neptune or a substantial super-Earth, makes the ongoing discovery of this exoplanet vastly more thrilling for scientists. We can state with a high degree of confidence that planets highly similar to our own Earth do exist within the Alpha Centauri system. However, the primary question that remains on everyone's mind is this: could human beings ever realistically travel there and live in that system? Without a doubt, the most daunting and difficult hurdle in our ongoing pursuit to establish a brand new home within the Alpha Centauri system would be the sheer, mind-boggling physical distance required to reach these 3 stars. Even though Alpha Centauri holds the crown as the closest star system to our planet, it is still positioned more than 4 light-years away from us. When translated into standard driving distances, that equals roughly 23.5 trillion miles, or approximately 37.8 trillion kilometers. To bridge such an immense cosmic void in a practical time frame, human engineers would need to build a fundamentally faster class of spacecraft, or discover an entirely new method of space transportation. According to official data from NASA, the retired Space Shuttle Discovery, which finished its service back in the year 2011, could achieve a maximum flight speed of about 17,500 miles per hour. Even if a spacecraft could maintain that exact speed continuously, a journey to Alpha Centauri would still require more than 148,000 years to complete. NASA also notes that even when the modern Orion spacecraft, the specialized crew capsule built for the ongoing Artemis lunar program, is fully ready to carry human passengers, its absolute maximum velocity will top out at approximately 20,000 miles per hour. This slight increase in speed will not do anything to significantly lower the immense travel time required to cross over to Proxima Centauri. Furthermore, that extreme timeline assumes either of these vehicles was actually engineered to fly into deep interstellar space, rather than being built to complete relatively short trips to our moon or to Mars. As we have previously discussed, the solitary spacecraft that have successfully crossed out of our solar system up to this point are the Voyager 1 and Voyager 2 probes. Even while travelling at their absolute maximum cruising speed of over 35,000 miles per hour, it will still take these probes nearly 40,000 years just to cross a distance of 2 light years. That distance will only bring them to the faint, ambiguous boundary line that separates our solar system from Proxima Centauri. This reality implies that it could easily take these automated spacecraft more than 80,000 total years to finally arrive anywhere near the actual star. After all, it requires a beam of light, the fastest moving thing in the universe, more than 4 full years, just to make the trip to Alpha Centauri. In order for a human-made spacecraft to reach a distant star system in a reasonable frame of time, such as within a single human generation, the vehicle must be engineered to be incredibly small and entirely robotic. In addition, it would still require an unimaginably powerful launch energy boost to accelerate it up to the necessary cruising speeds. This exact premise forms the foundation of the innovative Breakthrough Starshot project. The core concept involves manufacturing a specialized nanocraft called a star chip that is fitted with an ultralight space sail, which would first be launched into a stable orbit around the Earth. Once in orbit, a large mothership would deploy these miniature probes one by one, allowing them to catch and ride the highly concentrated beams fired from a massive, ground-based laser array. However, the primary engineering challenge for this concept is the Earth's thick atmosphere, which naturally bends and distorts laser light, as well as incoming starlight, making it incredibly difficult to deliver the precise physical push required to accelerate the spacecraft forward. To overcome this hurdle, the project plans to use small lasers mounted on orbiting satellites to analyze atmospheric distortions in real time. This data will allow much more powerful ground-based lasers to maintain a perfectly tight focus on the sailing spacecraft. To successfully launch the vessel into deep space at the required speeds, the ground lasers need to unleash a staggering 100 gigawatts of total power, an amount of energy that is roughly equal to the combined electricity usage of the entire United States. Fortunately, the laser array only needs to operate at this maximum power level for about 10 consecutive minutes per launch. The engineering plan involves linking up 100 million individual lasers to safely distribute this massive electrical load across a surface area measuring 1 square kilometer. The Starshot engineering team is completely dedicated to shattering the existing boundaries of space travel. Once those ground-based lasers are finally powered down, the miniature probe racing through the void of space will be flying at a jaw-dropping velocity equal to 20% of the speed of light. That equals a blistering speed of more than 130 million miles per hour, or approximately 216 million kilometers per hour. Built with a physical diameter measuring just a little bit over 10 meters, this specialized sailcraft could successfully cross the distance to Alpha Centauri in roughly 22 years. However, there is a chance it could be noticeably slowed down along the way by the inward gravitational pull of our Sun, as well as collisions with random interstellar debris particles. Even if the probe successfully reaches the Alpha Centauri system and gathers data, it will still take an additional 4 years for its broadcast signals to travel across the void and reach our receivers on Earth. It is interesting to note that Alpha Centauri is currently on a trajectory that brings it toward the Earth, though this movement is happening extraordinarily slowly and does not represent any kind of urgent threat to our world. As of the year 2024, the physical distance separating Alpha Centauri from the Earth sits at approximately 3.26 light-years. The system will make its absolute closest approach to us in the distant year 29,700 AD, at which point it will be located roughly 3 light-years away. Over the course of a standard human lifetime, this incredibly slow shift in distance will produce absolutely no visible or physical impact on the Earth or the wider solar system. Space is truly an extraordinary and mind-boggling territory, and human beings are uncovering brand new insights about its nature every single day. Leaving the Alpha Centauri system behind us, we continue our outward journey through the dark to arrive at Barnard's star, which holds the title of being the second closest star system to our Sun, sitting at a distance of roughly 5.95 light-years away from us. This star was officially named in honor of Edward Emerson Barnard, the American astronomer who originally made the discovery of the object back in the year 1916. Boasting an estimated cosmic age of anywhere between 11 and 12 billion years, which is roughly double the age of our own Sun Barnard's star, is an exceptionally ancient celestial body, and it is highly likely a member of the Milky Way's thick galactic disk population. Red dwarf stars that are relatively young or middle-aged typically rotate at a fast enough speed to generate intensely powerful internal magnetic fields, which frequently erupt in violent stellar flares that can instantly double the star's overall brightness. However, because Barnard's star was considered to be far too ancient, astronomers assumed it was incapable of displaying this kind of active behavior. In spite of that long-held assumption, on July 17th in the year 1998, a scientist named Diane Paulson, alongside her research colleagues working at NASA's Goddard Space Flight Center, shocked the astronomical community by revealing that a powerful solar flare had been unleashed by Barnard's star. Right when this unexpected event occurred, the star's unique light spectrum was being actively captured by William Cochran of the University of Texas at Austin, who is utilizing the 2.7-meter telescope located at the McDonald Observatory. His initial goal in gathering this data had been to search for subtle orbital variations that would hint at the presence of hidden planets circling the star. Instead, he unexpectedly caught bright emission lines flaring up across the spectrum, providing clear proof that the ancient star was undergoing a violent eruption. 4 years later, a deeper investigation carried out by Cochran's research team conclusively demonstrated that this hot blue stellar flare was remarkably identical to the powerful eruptions typically seen on much younger red dwarf stars, even though this particular star was incredibly old. The calculated temperature of this flare reached a blistering baseline of at least 8,000 Kelvin, a figure that was more than twice as hot as the star's normal surface temperature of 3,100 Kelvin. As Barnard's star steadily makes its structural way closer to our planet, its literal physical separation from us is continuously shrinking by roughly 0.036 light-years with the passing of every individual century. This movement occurs at an exceptionally rapid cosmic velocity of roughly 108 kilometers per second, which easily translates to an incredible 67 miles per second. Based on these calculations, the star's absolute closest point of approach to our central sun is mathematically projected to hit its limit at a distance of a mere 3.85 light-years, a landmark event that will transpire in the exceptionally distant future year of 11,800 AD. When evaluating its overall path across the sky, which astronomers formally refer to as proper motion, Barnard's star confidently holds the distinct record of being the absolute fastest moving stellar object across the entirety of Earth's visible night skies. Another fascinating structural attribute that makes Barnard's star completely unique within the field of modern astronomy is that it possesses the largest measurable proper motion of any star ever catalogued by human observers. This movement shifts at an impressive rate of approximately 10.4 arcseconds during the course of every single year, a value that accumulates to equal the entire visual diameter of our moon once every 180 years. Due to the unique combination of this dramatic swiftness and its extreme physical closeness to our home solar system, this star serves as an absolutely perfect target for researchers seeking to discover alien exoplanets. Any regular gravitational variations or subtle systemic wobbles in its continuous path across the dark canvas of space, generated by the pulling force of orbiting worlds, would naturally show up much more clearly to our monitoring equipment. After many years of focused observation, a dedicated alien planet was finally located circling around Barnard's star in the year 2018. This world follows a regular 233-day orbital pathway at an average tracking distance of roughly 60 million kilometers, which equals about 37 million miles away from its parent star. It boasts an overall physical mass that measures at least 3.2 times greater than our own Earth. However, this planet is explicitly not located inside the star's habitable zone due to the incredibly low light and energy output of its host red dwarf. This reality means that any water present on its alien surface would almost certainly be completely frozen solid. As we push our exploration even further away into the deep dark, navigating out to a distance of approximately 8.6 light-years from Earth, right near the familiar boundary of the constellation Orion, we eventually discover the star Sirius. Frequently referred to by stargazers as the prominent dog star, or officially designated as Sirius A, this magnificent cosmic beacon ranks as the absolute brightest star visible anywhere in Earth's entire night sky. Possessing a total material mass that is exactly twice as heavy as our own Sun, Sirius features a massive physical diameter tracking at roughly 1.5 million miles, which converts to approximately 2.4 million kilometers. If the star Sirius were to be artificially moved from its current cosmic position and placed directly alongside our central sun, its extreme brightness would easily outshine our home star by an astonishing factor of more than 20. Sitting gracefully within the structural borders of the Canis Major constellation, Sirius is actually a binary star system rather than a single solitary entity. The historic name for this star originally comes from the ancient Greek word Sirios, a term that literally translates to glowing brightly or scorching hot. Burning fiercely with an intense surface temperature that reaches nearly 18,000 degrees Fahrenheit, Sirius displays a distinct beautiful bluish colour tint and pumps out a level of energy that is 25 times more radiant than our Sun. It can be seen shining with absolute clarity during the winter night skies across the Earth's northern hemisphere. Because of this extreme visual brilliance, ancient human civilizations were deeply familiar with Sirius for thousands of years. Even so, professional astronomers were caught completely off guard when an unseeable companion star, officially named Sirius B, was unexpectedly discovered right next to it in the year 1862. While the primary star Sirius A is entirely visible to the naked human eye, its hidden partner Sirius B is a staggering 10,000 times fainter and completely impossible to detect without specialized equipment. Thanks to incredibly precise historical information captured by the Hubble Space Telescope, modern researchers were finally able to calculate the actual mass of this exceptionally dim object in the year 2005, despite the reality that it remains incredibly difficult to observe from Earth's surface. When we expand our focus to analyze the local cosmic neighborhood resting within a boundary of 20 light-years around our Sun, we find a total of roughly 131 distinct celestial objects. This diverse population includes traditional burning stars, failed stars known as brown dwarfs, and even smaller sub-brown dwarfs. Among this local collection, a mere 22 individual stars possess enough inherent brightness to be spotted by an observer without using a magnifying telescope. This means their visible light output must register at an apparent magnitude of at least +6.5, which marks the absolute limit of brightness that the human eye can naturally perceive from Earth. These 131 recognized celestial objects are structurally organized into 94 independent stellar systems. Breaking this down further, 103 of these objects are categorized as main sequence stars, which includes 23 typical high-mass stars and 80 small red dwarfs. In addition to these traditional suns, researchers have successfully logged the presence of 21 brown dwarfs, along with one solitary sub-brown dwarf designated as WISE 08550714, which scientists suspect might actually be a wandering rogue planet. Finally, this neighborhood contains 6 white dwarfs, which are the super-dense remnants of ancient stars that have completely burned through their entire internal supplies of fusible hydrogen fuel. An exceptionally rare cosmic event occurred roughly 70,000 years ago, when a red dwarf candidate system known as Schultz's star, travelling alongside its companion brown dwarf partner, passed directly through the absolute outer edge of our solar system's Oort cloud. At the present moment, this star system has travelled to a distance of approximately 22 light-years away from our Sun. However, its historic close passage likely disturbed the gravitational balance of countless frozen bodies, triggering a massive comet storm that will require over 1 million years to finally drift into the inner solar system. The structural orbits of various icy objects inside the distant Kuiper belt were also visibly altered by this star's ancient journey. Modern researchers have also spent a significant amount of time studying alternative stars that made similar close approaches, such as the G-type star, officially labelled HD 7977. This particular star made its closest historic flyby approximately 8 million years ago, and it is currently positioned at a safe distance of about 247 light-years away from our planet. Of course, ancient historical flybys are not the only cosmic interactions that human beings need to think about. There will be a significant number of new stars arriving in our immediate celestial neighbourhood in the future. Over the course of the next 15 million years, a total of 694 individual stars are mathematically predicted to make a close approach to our solar system, coming within a distance of less than 516 light-years. This detailed forecasting is based entirely on high-precision data collected during the Gaia Space Telescope's second major information release. Out of this group, 26 of those stars are on pathways that will likely bring them within an intimate distance of 3.3 light-years, and 7 more will close the gap to less than 6 light-years. Because of the sheer overwhelming quantity of stars across the galaxy that still need to be actively surveyed, the true number of future planetary visitors is probably vastly higher than these current estimates. To help put this into perspective, a star that was actively approaching our solar system 10 million years ago would be located anywhere from 600 to 6,000 light-years away from the Sun today, whereas millions of entirely different stars are now continuously drifting closer to our home system. Among the most famous and heavily documented examples of a close future stellar passage is the star known as Gliese 710. This is an orange star that possesses roughly 60% of the physical size of our Sun, and it can currently be located inside the borders of the Serpens constellation. This star is actively racing directly in our direction at a continuous velocity of 5,499 kilometers per hour, which equals nearly 32,000 miles per hour. In approximately 1.29 million years, its path will bring it to its absolute closest point to the Sun, passing at a distance of roughly 10,520 astronomical units. While that distance is still more than 100 times further out than the orbit of Pluto, which circles our Sun, at an average distance of 39.5 astronomical units, it still carries an immense potential to disrupt the gravitational stability of our solar system. If human beings are still thriving on Earth at that incredibly distant point in time, we will not need to stress about any major alterations to our planetary orbit. If Gliese 710 causes any noticeable gravitational effects at all, those changes will be restricted entirely to the freezing outer realms of the solar system, leaving everything operating inside the 40 astronomical unit mark completely untouched. Even so, the incoming star could easily trigger massive structural disruptions inside the Oort cloud, because it has an incredibly high statistical probability of sailing directly through that fragile comet repository. As a direct result of this penetration, intense comet showers would be continuously hurled inward toward the Sun for millions of consecutive years. This phenomenon would likely treat future skywatchers to the spectacular sight of roughly 10 bright comets visible to the naked human eye during every single year. These ongoing scientific searches for stars drifting close to our Sun do not just offer an excellent opportunity to discover ancient comets, they also allow us to predict an incredibly thrilling future for any visual observers living on Earth thousands or millions of years from now. At this very moment, our entire solar system, alongside our neighbouring collection of stars and dwarf systems, is actively travelling through or resting right near the edge of a structure known as the local interstellar cloud, which spans roughly 30 light-years across. This local interstellar cloud is itself completely enclosed within the much larger local bubble, which is a massive hollowed-out cavity carved into the interstellar medium that stretches approximately 1,000 light-years across and features a highly unusual, peanut-like physical shape. Our Sun was located extremely far away when this giant bubble was initially blown open by ancient supernovae, roughly 14 million years ago. However, approximately 5 million years ago, the continuous galactic pathway of our solar system naturally drifted directly into the interior of this cosmic void. Interestingly, new stars have successfully formed all along the dense outer surface of this bubble, but absolutely no star formation occurs inside its hollow interior. There are currently 7 active star-forming regions positioned right around the outer shell of this bubble. It is precisely because of the unique environment provided by this local bubble that the continuous evolution of complex life has been able to safely unfold on Earth today. As we push our voyage significantly further away from home, we eventually arrive at the majestic Orion constellation, which sits at a distance of around 1,344 light-years away from Earth. As a quick reminder, a single light-year represents the total physical distance that a beam of light can travel over the course of 1 year, a value that equals roughly 6 trillion miles, or approximately 10 trillion kilometers. The Orion constellation is recognized as one of the 88 modern official constellations in astronomy, and its name is derived from a famous giant hunter from ancient Greek mythology. The broader structure contains well over 60 individual stars, a population that includes the prominent star Betelgeuse. Betelgeuse is a massive red supergent star located at a distance of roughly 650 light-years away from us. It ranks as one of the single largest stars known to science, boasting an absolutely mind-boggling physical diameter of about 767 million miles, which translates to roughly 1.2 billion kilometers. This size makes it roughly 700 times larger in physical dimensions than our Sun, while its overall material mass tracks at anywhere between 10 and 20 times the mass of our home star. Because Betelgeuse may currently have less than 300 years worth of nuclear fuel remaining inside its core, a non-stop debate has broken out among researchers across the globe regarding exactly when it will undergo a violent explosion. The moment the star's core finally burns through its very last drops of fuel, it will instantaneously collapse into a dense black hole, blasting its massive outer layers into the void at extreme speeds, reaching up to 25,000 miles per second, or roughly 40,000 kilometers per second. Astronomers formally refer to this kind of radiant, violent demise as a supernova explosion. In the specific case of Betelgeuse, this event will provide a truly breathtaking spectacle for human observers on Earth. The expanding layers of illuminated gas and cosmic dust will shine fiercely in our night sky for several consecutive weeks, generating a level of brightness that will easily match the full moon, simply because the star is located a mere 650 light-years away from our planet. The main catch is that the vast majority of professional astronomers do not believe that Betelgeuse is actually ready to undergo a massive explosion anytime soon. Instead, skywatchers typically expect that it will detonate sometime within the next 100,000 years, a timeline that represents an immediate flash on a cosmic scale, but an incredibly long duration on a human time frame. Another highly famous collection of stars resting inside this constellation forms the straight line known as Orion's Belt, which is made up of 3 distinct stars situated right across the midsection of the Orion structure. Moving across the sky from east to west, these 3 stars are officially named Alnitak, Alnilam, and Mintaka. This distinct belt represents what is arguably the single most recognizable pattern within the Orion constellation, because it can be easily spotted from locations all around the world. Taken individually, these 3 supergent stars are separate cosmic powerhouses that burn thousands or even tens of thousands of times brighter than our Sun, while also being several times more massive. Even though these 3 stars appear to sit incredibly close to one another from our perspective on Earth, they are actually separated by immense distances of empty space. Orion's belt is primarily utilized by stargazers as a vital celestial landmark when trying to locate M42, which is widely known as the famous Orion Nebula. Positioned directly underneath the Hunter's belt, M42 stands out as one of the most visible Messier objects for amateur astronomers, because it is exceptionally easy to locate and observe using a basic backyard telescope or even a standard pair of binoculars. Looking directly into this structure is exactly like peering into a grand celestial nursery where brand new stars are actively being brought to life. The Orion Nebula represents one of the single largest clouds of gas and interstellar dust residing anywhere within our home Milky Way galaxy. It possesses an estimated cosmic age of approximately 2 million years and is located roughly 1,300 light-years away from Earth. Because this magnificent nebula exhibits an apparent visual brightness of +4 on the standard astronomical magnitude scale, it can actually be detected by the unaided human eye under dark skies. For context, on this magnitude scale, a value of +6 represents the absolute faintest object that can be perceived by human eyes under the absolute best lighting conditions. Stretching across a massive physical diameter that measures between 30 and 40 light-years, this colossal nebula could currently be fostering the birth of over 1,000 individual stars. Resting deep within the interior of the nebula is a young, open star cluster whose member stars are still only loosely bound to one another by the weak pull of gravity, having all formed at the exact same time from the surrounding gas cloud. This structure is frequently referred to by skywatchers as the Orion Nebula Star Cluster. An international coalition of professional astronomers proposed a fascinating theory in the year 2012, suggesting that this central cluster inside the Orion Nebula might actually hide a black hole right at its core. When looking through simple low-power telescopes, observers can easily distinguish the 4 brightest stars nestled inside the heart of the Orion Nebula, a tight stellar formation collectively known as the trapezium. The entire surrounding expanse of the Orion Nebula is illuminated by the intense, hot light pouring out of these young trapezium stars. When evaluated in terms of typical stellar life cycles, these stars are exceptionally young, having existed for a total duration of only about 1 million years. Just last year, the Advanced James Webb Space Telescope captured a detailed infrared image of the Orion Nebula. This stunning image reveals a violent explosion of cosmic dust, newborn stars, and dense clouds rendered in brilliant shades of red, purple, and blue, all contrasting sharply against the cold background of deep space. Additionally, the James Webb Telescope successfully discovered a total of 540 planetary mass objects drifting within the nebula, featuring individual masses that range from 0.6 times the mass of Jupiter up to the size of Jupiter itself. Among this newly discovered population of planetary mass objects, the single most fascinating targets are the Jupiter mass binary objects, which are unique because they do not exist as solitary worlds orbiting through space on their own. Our home Milky Way galaxy is formally classified as a spiral galaxy. By definition, a spiral galaxy is a massive stellar structure that resembles a flattened, rapidly rotating disk featuring a prominent spherical bulge at its center, with majestic spiral arms extending gracefully outward from that central core. While our independent spiral galaxy contains a multitude of smaller minor arms alongside just 2 primary major arms, astronomers traditionally believed for many years that the system featured 4 major arms. However, Modern scientists have successfully demonstrated that just two primary arms, wrapping neatly off the outer tips of a thick central bar of stars, completely dominate the Milky Way's beautiful spiral layout. These major structural discoveries were made possible through the utilization of NASA's Spitzer Space Telescope, which allowed researchers to peer through blocking dust using advanced infrared imagery. The two major arms of our galaxy, officially named the Scutum Centaurus arm and the Perseus arm, connect directly to the tips of this thick central stellar bar. Meanwhile, the two minor arms that were officially demoted by scientists, named Norma and Sagittarius, are positioned in the spaces between the major arms and appear significantly less distinct. While these minor arms are composed primarily of raw gas and active pockets where new stars are forming, the two major arms contain the absolute highest concentrations of both young and ancient stars. Radio astronomers utilize massive ground-based telescopes to carefully track the precise movements of the giant hydrogen clouds that map out these arms. Tracing a spiral path with a pitch angle of approximately 9 degrees, the massive Perseus arm features a long spiral extension and measures well over 60,000 light-years in total length and 1,000 light-years in width. This arm contains the famous Crab Nebula alongside well-known double-star clusters. On the other side of the galaxy, the Scutum Centaurus arm stretches for roughly 55,000 light-years in length and maintains a physical width of about 1,000 light-years. Our own solar system resides in the space separating two of these prominent spiral arms, specifically positioned between the Perseus arm and the Scutum Centaurus arm. However, we are not completely isolated or free-floating in an empty galactic void. Instead, our system is situated right on the outer edge of the Orion Cygnus arm. Frequently referred to by astronomers as simply the Orion arm or the local arm, this is a relatively minor spiral arm. This smaller spiral structure spans a length of approximately 10,000 light-years and features a physical diameter of about 3,500 light-years. Even so, a detailed scientific analysis published in the year 2016 indicates that its true length might actually exceed 20,000 light-years. The Orion arm is named directly after the prominent Orion constellation. Our solar system is located within the local bubble, right along the inner edge of this Orion arm structure. This tracking position places us at a distance of roughly 26,000 light-years away from the galactic center, sitting about halfway down the overall length of the Orion arm. You might be completely surprised to learn that it requires our Sun roughly 250 million years just to finish one single orbital revolution around the center of the Milky Way. Astronomers formally refer to this immense duration of time as a single cosmic year or a galactic year. Because of this extreme timeline, scientists estimate that during its entire multi-billion-year lifespan, our Sun has managed to finish only 18 to 20 full orbits around the galaxy. Since the historical dawn of the human race, our solar system has been racing around the Milky Way center at a continuous speed of about 220 kilometers per second, a velocity that equals roughly 0.73% of the speed of light. Travelling at this extreme speed, it takes our solar system around 4,900 years to cross a distance of one single light year, or about 8 full days to cross a distance equal to 1 astronomical unit. Following along the path of the ecliptic, our solar system is actively travelling toward the zodiacal constellation Scorpius. The very last time our solar system sat in this exact same physical position within the Milky Way galaxy, dinosaurs were still actively roaming across the surface of the Earth. Who can truly say what will be happening when our system arrives back at this position next? Humanity might be completely extinct, or our species might have evolved into something else entirely. Our specific structural location within the wider galaxy is incredibly important because it appears that entire galaxies possess distinct habitable zones, much like independent planetary systems do. Because a vast number of the Milky Way's suns orbit the galaxy along hazardous pathways that force them to pass directly through the deadly crowded environment of the spiral arms, an astonishing 95% of all stars in the galaxy may be entirely incapable of supporting habitable planets. The intense radiation pouring out of these crowded stellar environments is completely lethal for any star system that passes through one of these dense stellar swarms. In order to maintain its safe alignment with the broader rotation of the galaxy, our solar system was blessed with an orbit positioned sufficiently far away from the galactic center. This allows us to remain permanently inside the calm, peaceful region that sits safely between the violent spiral arms. Nestled within a massive and incredibly intricate galaxy, the Earth and its planetary siblings are beautifully situated inside a quiet, resource-rich cosmic neighborhood. As we continue to navigate through the expansive lanes of our galaxy, we leave behind the serene interstellar spaces that sit comfortably between the spiral arms of the Milky Way. Our celestial journey now takes us significantly closer to the deeply mysterious and densely packed inner core of our cosmic home. Travelling a vast distance of approximately 9,500 light-years away from the planet Earth, we enter the structural boundaries of the constellation Scutum. It is within this specific region of deep space that we encounter a truly mind-boggling stellar phenomenon known to the global scientific community as UY Scutum. This cosmic entity holds a highly distinguished position in the fields of modern astronomy, as it is widely recognized by researchers to be one of the single largest stars currently known to exist anywhere in the observable universe. To comprehend the unbelievable physical proportions of this star, we must analyze its structural dimensions. UY Scutum boasts an incredible solar radius that measures out to a staggering 1.18 billion kilometers. When compared directly to the central star of our own planetary neighborhood, this means that the radius of UY Scutum is roughly 10,100 times larger than the physical radius of our Sun. If we were to calculate the absolute physical diameter of this hypergiant star using standard astronomical measurements, we would find that it stretches across a distance of more than 8 individual astronomical units. To put this into a frame of reference that is easier for human minds to process, one astronomical unit represents the standard distance between the Earth and the Sun, which converts to approximately 150 million kilometers, or roughly 93 million miles. Therefore, the physical body of UY Scutum spans a distance equivalent to 8 times the orbital gap separating our home planet from our central star. If an imaginary cosmic architect were to suddenly pluck UY Scutum from its current location in the Scutum constellation and drop it directly into the heart of our solar system to replace our Sun, its sheer, overwhelming physical size would completely transform our planetary neighborhood. The outer surface and burning edge of this colossal star would instantly swallow Mercury, Venus, Earth, and Mars. Moving even further outward, its massive body would expand so far into space that it would easily reach well past the orbital path of Jupiter, which circles our Sun at a distance roughly 5 times greater than the Earth's orbit. The staggering dimensions of UY Scutum are not restricted solely to its visible stellar surface. The immense cloud of gas nebula that is continuously being pushed and ejected from the outer layers of the star stretches into the surrounding void for an unbelievable distance. This stellar shroud extends out to a length that is 400 times greater than the distance between the Earth and the Sun. This means the star's personal gas cloud reaches incredibly far out into the deep dark, expanding past the cold, distant orbit of Pluto and pushing way beyond the traditional boundaries of our outer solar system. To visualize this dramatic cosmic scale in another way, we can look at the physical volume of these bodies. Everyday human experience teaches us that the Earth is a massive world, and indeed, more than 1 million individual Earths could comfortably fit inside the interior volume of our Sun. However, if you were to construct a giant hollow sphere matching the exact physical size of UY Scutum, it would require an astonishing 5 billion individual suns packed together just to completely fill the inside of that cosmic structure. Because of these extreme physical proportions, professional astronomers officially classify UY Scutum as a hypergiant star. This rare stellar designation represents the absolute highest tier of star classification, sitting well above the traditional categories of supergiant stars and standard giant stars. However, an important scientific distinction must be made regarding the relationship between a star's physical size and its actual material weight. While UY Scutum may currently claim the crown as one of the largest stars in terms of its structural volume, it is explicitly not the heaviest or most massive star catalogued by human observers. Within the field of physics and astronomy, the term mass refers specifically to the total amount of physical matter contained inside an object. When we shift our focus to look for the single heaviest star ever discovered in the cosmos, the title goes to a completely different star system designated as R136A1. This dense stellar powerhouse weighs in at an incredible mass that is roughly 300 times heavier than our Sun. Yet in terms of its physical dimensions, R136A1 features a radius that is a mere 40 times larger than the radius of our Sun. UY Scutum presents the exact opposite physical setup. It possesses a structural size that dwarfs our Sun completely, but its actual material mass is estimated to be only between 7 and 10 times greater than the mass of our home star. In a similar fashion, possessing such a massive physical volume does not automatically mean that UY Scutum burns with an intensely hot surface. In reality, the measured temperature across the outer surface of this hypergiant is surprisingly low, registering at almost half the surface temperature of our own Sun. Another fascinating structural attribute that makes UY Scutum a major target for ongoing research projects is that it operates as a classic variable star. When astronomers monitor this star over long periods of time, they can clearly detect regular variations and noticeable shifts in its overall visual brightness. These changes in light output are a direct result of the raw material continuously shifting, expanding, and contracting at and near the star's surface. This constant structural movement is generated by an unstable, ongoing internal battle between the inward crushing force of gravity and the outward pushing force of nuclear fusion occurring deep within its core. These types of volatile stars are of special interest to professional astronomers across the globe because studying their behavioral patterns can shed vital light on the complex inner workings and evolutionary life cycles of massive stars. While some researchers believe that UY Scutum, like many other large stars across the Milky Way, might be fully capable of supporting its own independent planetary system, the extreme life cycle of the star makes the survival of close worlds completely impossible. It is highly likely that any innermost exoplanets that may have originally formed around this star were completely swallowed up and destroyed long ago when the host star entered its current hypergiant phase of extreme physical expansion. Furthermore, because UY Scutum is located so far away and appears so dim to our monitoring equipment from Earth, it is highly improbable that human engineering will ever develop telescopes advanced enough to directly witness or capture images of any surviving outer exoplanets circling this distant giant. Leaving the massive burning bulk of UY Scutum behind, we push our voyage even deeper toward the exact structural center of our home Milky Way galaxy. Navigating a profound distance of approximately 26,000 light-years away from our planet, we finally come face to face with an absolute celestial enigma known to science as Sagittarius A. This supermassive black hole is an incredible cosmic monster that completely defies everyday human understanding, existing as a point of infinite density that acts as the primary gravitational anchor for our entire spinning galaxy. As we move closer to this dark heart of the Milky Way, we find ourselves entering a truly chaotic and extreme environment where the traditional laws of physics are pushed to their absolute limits. The space surrounding Sagittarius A is packed with incredibly dense clusters of ancient stars, high-energy cosmic radiation, and massive streams of swirling interstellar gas, all trapped in a frantic orbital dance around an invisible point of no return. To understand the sheer power of Sagittarius A, we must look at its mathematical properties. This cosmic entity packs the physical mass of roughly 4.3 million suns into a region of space that is incredibly compact by cosmic standards. Because of this concentrated mass, its gravitational pull is so monumentally strong that nothing, not even a beam of light traveling at the absolute speed limit of the universe, can ever escape its grasp once it crosses the invisible boundary known as the event horizon. For many decades, the existence of this supermassive black hole was something scientists could only infer by carefully tracking the highly unusual hypervelocity orbits of nearby stars that appeared to be circling around an empty patch of void. However, in a historic triumph for human engineering and international scientific collaboration, the Event Horizon Telescope project successfully captured the very first direct visual image of Sagittarius A. This incredible image revealed a dark central shadow surrounded by a glowing ring of superheated gas and plasma, moving at near light speeds as it is continuously pulled toward the black hole's maw. The space surrounding Sagittarius A is also home to an intense field of stellar remnants, including highly magnetized neutron stars known as magnetars and rapidly spinning pulsars that act as cosmic lighthouses, blasting out beams of intense radiation across the galaxy. The continuous study of this extreme environment provides researchers with an unmatched natural laboratory for testing Albert Einstein's theory of general relativity under the strongest gravitational conditions possible. Every single star, planet, gas cloud, and living creature residing within the vast spiral arms of the Milky Way is ultimately bound to this central anchor, continuously orbiting around Sagittarius A in a grand galactic cycle that spans hundreds of millions of years. As we look outward from this central cosmic powerhouse, we begin to see the broader structure of our galaxy's core, which is packed with massive molecular clouds that serve as the primary fuel source for future generations of stars. These dense structures, often referred to as central molecular zones, contain enough raw gas and dust to forge millions of new suns. However, the extreme tidal forces generated by the proximity to Sagittarius A often rip these fragile clouds apart before they can successfully collapse under their own gravity to form new star systems. This creates a highly dynamic and cyclical environment where cosmic destruction and stellar creation are permanently locked in a non-stop struggle for dominance. Beyond the immediate vicinity of the supermassive black hole, the galactic center features an incredibly dense accumulation of stars known as the nuclear star cluster. This is recognized by astronomers as the single densest stellar environment found anywhere within the entire Milky Way galaxy, containing tens of millions of individual stars packed into a region of space only a few light years across. If you were to stand on an imaginary planet located deep within this central cluster, the night sky would be completely illuminated by the brilliant light of thousands of stars shining significantly brighter than the full moon appears from Earth, making total darkness an absolute impossibility. This extreme crowding also leads to frequent stellar collisions and close gravitational encounters, which can completely disrupt the orbital pathways of existing planetary systems or violently hurl solitary stars out of the galactic core entirely. These wandering outcasts, known as hypervelocity stars, are accelerated to such extreme speeds by their interactions with the central black hole that they are placed on pathways that will eventually break them completely free from the gravitational grip of the Milky Way, launching them into the vast, empty void of intergalactic space. By analysing the trajectories of these runaway stars, astronomers can effectively retrace their steps back to the galactic centre, gathering vital data about the hidden forces operating within the core. As we slowly transition away from the dense, high-energy environment of the galactic centre and begin our journey back out toward the wider disk of the galaxy, we encounter a completely different class of celestial objects that play a critical role in shaping the layout of the Milky Way. These are the globular clusters, which exist as massive, tightly bound spherical swarms containing hundreds of thousands or even millions of ancient stars. Unlike the young, open star clusters found nestled within the gas-rich environments of the spiral arms, globular clusters are primarily composed of some of the absolute oldest stars in the entire universe, with ages that closely approach the timing of the Big Bang itself. These ancient systems orbit the galaxy along highly elongated, elliptical pathways that take them far above and below the flat galactic plane, forming a vast spherical halo that completely envelops the Milky Way. Because these globular clusters formed during the earliest developmental stages of our galaxy, before successive generations of exploding supernovae could enrich the interstellar medium with heavier chemical elements, their member stars possess an incredibly low metal content. In the language of astronomy, any element heavier than hydrogen and helium is classified as a metal, and the lack of these complex materials inside ancient cluster stars provides scientists with a pristine, unaltered window into the chemical composition of the early cosmos. Studying the precise ages and distribution of these globular clusters allows researchers to systematically reconstruct the complex historical timeline of how the Milky Way was originally assembled billions of years ago. Moving through the outer halo and back down into the main stellar disk, we start to observe the intricate ways in which cosmic dust and interstellar gas interact to create the breathtaking visual structures that define our galaxy. The vast spaces separating individual star systems are explicitly not empty voids. Rather, they are filled with an incredibly complex network of diffuse matter known as the interstellar medium. This material is constantly being recycled and transformed by the stars themselves. Young, high-mass stars continuously pump out intense stellar winds and torrential streams of ultraviolet radiation that carve out massive bubbles and intricate cavities within the surrounding gas clouds. When these short-lived giant stars eventually reach the end of their life cycles and detonate as violent supernovae, they hurl their enriched outer layers deep into the void, seeding the interstellar medium with the vital heavy elements necessary to forge future generations of rocky planets and ultimately the building blocks of organic life. This ongoing cycle of stellar death and rebirth creates a highly interconnected cosmic ecosystem where the past generations of stars directly determine the physical characteristics and habitability of the systems that succeed them. The beautiful spiral arms of the Milky Way act as massive density waves that continuously plough through this interstellar material, compressing the diffuse gas and triggering widespread bursts of new star formation along their leading edges. As we chart our course through these vibrant star-forming regions, we gain a profound appreciation for the delicate balance of physical forces that allows a galaxy to continuously evolve over billions of years, transforming raw primordial elements into a structured, complex haven capable of fostering conscious observers who can look back out and wonder at the majesty of their cosmic home. Deep within the highly energetic, crowded core of the Milky Way, we observe a collection of unique objects that hold a very high significance for researchers looking to calculate the true evolutionary background of our galaxy. Moving out from the central regions, we find that the local interstellar cloud, which measures an impressive 30 light-years across its entire physical length, is the exact local pocket of space through which our entire solar system, along with its neighbouring stars and brown dwarfs, is currently moving. When we map out this local neighbourhood on a grander structural scale, we discover that this local cloud is nestled safely inside a much larger cosmic feature, known to science as the local bubble. This massive structure exists as a vast, hollow cavity cleared out within the wider interstellar medium, stretching out across a physical distance of approximately 1,000 light-years from one side to the other. Interestingly, when astronomers map out the structural layout of this massive bubble, they find that it possesses a highly unusual, distorted shape that closely resembles a cosmic peanut. By tracking the movement of stars and gas through space, professional researchers have been able to trace the deep historical timeline of this local bubble, revealing that it first began to take shape roughly 14 million years ago, when a series of powerful supernovae detonated in this region of space. At that specific point in ancient history, our own sun was located a very vast distance away from this region, completely uninvolved with the bubble's creation. However, as the sun continuously travelled along its standard orbital pathway around the centre of the galaxy, its forward motion eventually brought it across the threshold and directly into the interior space of the local bubble approximately 5 million years ago. An incredibly fascinating detail regarding this cosmic structure is that star formation does not occur within the hollow interior of the bubble itself. Instead, the compression of gas along its expanding outer edges has triggered widespread starbirth. Astronomers have successfully identified exactly 7 distinct star-forming regions situated directly along the surface of this local bubble. Many astrobiologists believe that the unique, cleared-out environment of this local bubble has played a highly critical role in protecting our planet from harsh cosmic radiation, thereby making the long-term development of complex biological life possible on Earth today. As we push our voyage significantly further out into the deep dark of the galaxy, leaving our immediate neighborhood behind, we eventually cross a vast distance to reach the famous Orion constellation, which sits approximately 1,344 light-years away from our home planet. To put this distance into a standard physical frame of reference that human minds can comprehend, a single light-year represents the absolute distance that a beam of light can travel over the course of one full calendar year, which converts mathematically to roughly 6 trillion miles, or approximately 10 trillion kilometers. The majestic constellation of Orion is recognized globally as one of the 88 modern official constellations used by astronomers to map out the night sky, and its name is deeply rooted in the ancient traditions of Greek mythology, where it represents a legendary hunter. When we analyze this constellation with professional scientific equipment, we find that it contains well over 60 individual prominent stars, including an absolute titan of the night sky known as Betelgeuse. This immense stellar entity is classified by astronomers as a red supergiant star and is situated at a distance of roughly 650 light-years away from Earth. Betelgeuse holds a highly distinguished reputation as one of the single largest stars currently known to exist anywhere in the observable cosmos, boasting a mind-boggling physical diameter that measures roughly 767 million miles, which translates to approximately 1.2 billion kilometers. To help visualize this unbelievable scale, if you were to place Betelgeuse next to our own central star, you would find that it is roughly 700 times larger than the physical size of our Sun, while its actual material mass is estimated to be between 10 and 20 times heavier than our home star. Because Betelgeuse has been burning through its internal fuel supply at an extremely frantic rate due to its massive size, professional astrophysicists across the globe are locked in a continuous, highly active discussion regarding exactly when it will completely exhaust its remaining resources and detonate. Current scientific estimates suggest that this aging giant may have less than 300 years of usable fuel left deep inside its core. Once those final remaining drops of hydrogen and helium are completely consumed, the star's immense core will instantly suffer a violent gravitational collapse, transforming into a dense black hole while simultaneously blasting the star's outer atmospheric layers out into the surrounding void of space at terrifying velocities reaching up to 25,000 miles per second, or roughly 40,000 kilometers per second. Professional astronomers refer to this type of violent, brilliant stellar demise as a supernova explosion. In the specific case of Betelgeuse, its death will provide observers back on Earth with an absolutely breathtaking, once-in-a-lifetime visual spectacle. The expanding, superheated layers of ejected gas and cosmic dust will burn so brightly in our night sky that they will remain clearly visible for several consecutive weeks, casting a luminous glow that will easily rival the brightness of a full moon, all because the star is located relatively close to us in the grand scheme of the galaxy. However, despite the popular excitement surrounding this impending cosmic event, the vast majority of professional astronomers do not believe that Betelgeuse is truly ready to experience this massive explosion in the immediate future. When scientists analyze the behavior of the star on a cosmic timeline rather than a temporary human timescale, they fully expect that it will detonate sometime within the next 100,000 years, meaning it is highly unlikely to occur during our current generation. Shifting our focus to another highly famous feature within this same constellation, we observe a striking alignment of stars known globally as Orion's Belt. This distinctive stellar line is composed of exactly 3 massive supergent stars positioned right around the physical midsection of the constellation which are designated from east to west as Aunitak, Aunilam, and Mintaka. This particular belt structure is widely considered to be perhaps the single most recognizable and easily identifiable stellar pattern found anywhere in the night sky, primarily because it remains clearly visible to observers looking up from almost any geographic location across the entire surface of the Earth. When we examine these three belt stars individually, we discover that each one burns thousands or even tens of thousands of times brighter than our own Sun, while also weighing several times more than our home star. Furthermore, while these three cosmic giants appear to sit shoulder to shoulder when viewed from our perspective on Earth, they are actually separated from one another by vast distances, stretching across multiple light years of deep space. Because of its high visibility and reliable positioning, Orion's belt is frequently utilized by amateur and professional astronomers alike as a critical celestial landmark to help navigate the surrounding night sky, especially when searching for a spectacular deep space object known as M42, or the Orion Nebula. This magnificent nebula is situated directly below the line of the belt and is widely celebrated as one of the single most visible and easily accessible Messier objects for beginner astronomers, as it can be effortlessly located and viewed using a basic backyard telescope or even a standard pair of consumer binoculars. Looking directly into the heart of M42 is an awe-inspiring experience that allows humans to peer into a literal celestial nursery, providing a first-hand view of the exact environments where brand new stars are continuously being born out of raw materials. The spectacular Orion Nebula stands out as one of the absolute largest and most massive clouds of gas and interstellar dust found anywhere within the structural boundaries of our entire Milky Way galaxy. Modern astronomical data reveals that this vibrant structure is approximately 2 million years old and sits at a physical distance of roughly 1,300 light-years away from the planet Earth. Because this magnificent nebula shines with a highly impressive apparent brightness of +4 on the standard astronomical magnitude scale, it is bright enough to be easily detected by the naked human eye under dark, clear skies. To understand how impressive this is, it helps to know that on the official astronomical magnitude scale, a value of +6 represents the absolute faintest, lowest brightness object that the human eye can possibly perceive under the most pristine lighting and atmospheric conditions available. This massive stellar nursery spans an incredible physical diameter of between 30 and 40 light years from side to side, and within this vast space, it contains enough raw material to comfortably give birth to well over 1,000 individual brand new stars. Nestled directly inside the dense core of the nebula is a young, open star cluster whose member stars are still only loosely held together by their mutual gravitational attraction, having all formed at roughly the same time from the exact same collapsing gas cloud. Because of its physical location, this grouping is frequently referred to by researchers as the Orion Nebula Star Cluster. In a fascinating scientific development that occurred in the year 2012, an international team of professional astronomers analysed the rapid movements of these stars and suggested that this young cluster might actually harbour a medium-sized black hole hidden deep within its central core. When observing this nebula through a standard small telescope, anyone can easily spot the four brightest and most dominant stars residing at its centre, which are collectively known as the trapezium. The entire surrounding structure of the Orion Nebula is illuminated and made to glow brilliantly by the intense, high-energy radiation blasting outward from these young, scorching, hot trapezium stars. In terms of standard stellar life cycles, these four central stars are considered to be incredibly young infants, having existed for a mere 1 million years. Just last year, the state-of-the-art James Webb Space Telescope directed its advanced instruments toward this region and captured a truly historic, highly detailed infrared image of the Orion Nebula. This spectacular image revealed a chaotic, breathtaking explosion of cosmic dust, newborn stars, and churning gas clouds glowing in vibrant hues of deep red, rich purple, and brilliant blue, all set against the absolute darkness of the surrounding outer space. In addition to these beautiful structures, The hypersensitive sensors of the James Webb Space Telescope successfully detected a total of 540 independent planetary mass objects drifting through the nebula, featuring individual masses that range from a modest 0.6 times the mass of Jupiter all the way up to the size of Jupiter itself. Among this large collection of free-floating planetary bodies, the objects that have most thoroughly fascinated the global scientific community are the Jupiter mass binary objects. These unique entities do not exist as solitary, isolated worlds drifting through space on their own. Instead, they are paired up in close couples, orbiting around one another as they float together through the stellar nursery. When we pull back our view to analyze the grand architecture of our entire cosmic home, we see that our Milky Way galaxy is structurally classified as a classic spiral galaxy. By definition, a spiral galaxy is a massive celestial structure that takes the physical form of a flat, rapidly rotating disk, featuring a dense, tightly packed bulge of ancient stars positioned directly at its center, with grand spiral arms extending gracefully outward from that central core. While there are a multitude of smaller, minor arms branching off throughout the system, astronomers for many decades traditionally believed that the Milky Way possessed exactly 4 major, equal spiral arms. However, as human technology advanced, researchers discovered that just 2 primary, dominant arms wrapping neatly off the outer ends of a thick central bar of stars actually dictate the beautiful spiral structure of our galaxy. These critical structural discoveries were made possible by the advanced infrared instruments on board NASA's Spitzer Space Telescope, which allowed scientists to peer directly through obscuring clouds of cosmic dust using detailed infrared imagery. These 2 primary high-density arms of our galaxy are formally designated as the Scutum Centaurus arm and the Perseus arm, both of which anchor directly into the outer tips of the thick central stellar bar. Meanwhile, the 2 minor arms, known as the Norma arm and the Sagittarius arm, have been officially demoted in status by astronomers because they sit less distinctly between the 2 major arms and possess a much lower concentration of stars. While these minor arms are primarily composed of loose pockets of gas and active regions where new stars are currently forming, the 2 major arms contain the absolute highest densities of both newborn, hot stars and ancient, long-lived stellar populations. To map out these massive structures, radio astronomers utilized giant ground-based telescopes to carefully track the precise movements of the massive hydrogen gas clouds that trace the paths of these arms through the dark. When we look at the specific dimensions of these features, we find that the Perseus arm features a distinct spiral extension and measures an incredible 60,000 light-years in total length, while spanning a width of roughly 1,000 light-years. This massive arm plays host to several famous cosmic landmarks, including the iconic Crab Nebula and the well-known Double Cluster. On the other side of the galaxy, the Scutum Centaurus arm boasts an equally impressive length of approximately 55,000 light-years, while maintaining a matching width of roughly 1,000 light-years across. When we look to find our own place within this grand galactic map, we discover that our solar system is situated in the relative calm between these 2 prominent, high-density spiral arms, sitting directly between the inner edge of the Perseus arm and the outer edge of the Scutum Centaurus arm. However, this does not mean that we are completely isolated or free-floating in an empty cosmic void. Rather, our planetary system is located directly along the inner edge of a smaller, secondary spiral structure known as the Orion Cygnus arm, which is also frequently referred to by astronomers as the Orion arm, or simply the local arm. For a long time, this minor spiral arm was thought to be a small spur, spanning a length of about 10,000 light-years and featuring a diameter of approximately 3,500 light-years. However, a detailed scientific analysis published in the year 2016 indicates that its true structural length may actually exceed 20,000 light-years, making it a much more significant feature than previously assumed. The Orion arm receives its formal name because it contains the prominent stars of the Orion constellation, and our solar system resides inside the local bubble right along the inner boundary of this arm. When we calculate our exact distance from the heart of the galaxy, we find that we are positioned roughly 26,000 light years away from the galactic center, placing us almost exactly halfway down the entire physical length of the Orion arm. Because our galaxy is constantly spinning through space, our Sun must continuously orbit around the central core of the Milky Way. You might be deeply surprised to learn that it takes our Sun an astonishing 250 million Earth years just to complete one single full rotation around the galactic center. Astronomers formally refer to this immense period of time as a single cosmic year, or a galactic year. Because this cycle is so incredibly long, scientists estimate that during its entire 4.6 billion year lifespan, our Sun has successfully completed only 18 to 20 full orbits around the galaxy. As we sit on our planet today, our entire solar system is hurtling around the Milky Way at a staggering speed of approximately 220 kilometers per second, which translates to roughly 0.73% of the absolute speed of light. Even at this breathtaking velocity, it still takes our solar system around 1400 years to travel a distance of just one single light year through space, or roughly 8 full days to cross a distance equivalent to one astronomical unit. Following its established path along the ecliptic plane, our solar system is currently travelling steadily toward the direction of the zodiacal constellation Scorpius. To help put this immense timeline into perspective, the last time our solar system occupied this exact same physical position in its galactic orbit, massive dinosaurs were still actively walking across the surface of the Earth. This realization naturally makes us wonder about the far-off future, as nobody can truly predict what will happen the next time we return to this spot. By then, humanity might be completely extinct, or our descendants may have evolved into something else entirely. Our precise physical positioning within the wider structure of the galaxy is incredibly important to the survival of our species, because recent astronomical data indicates that entire galaxies possess distinct habitable zones just like individual planetary systems do. Because a vast number of the suns residing within the Milky Way orbit the galactic center along highly volatile paths that repeatedly take them directly through the dense, high-energy environments of the main spiral arms, an astounding 95% of all stars in the galaxy may be completely unable to safely support habitable planets. The intense, concentrated radiation blasting outward from the crowded star clusters inside those main arms is completely deadly to the atmosphere of any planet travelling through those stellar swarms. In sharp contrast, our solar system is perfectly situated because it orbits sufficiently far away from the chaotic galactic center, allowing us to stay permanently nestled within the calm, quiet, and peaceful region that sits safely between the deadly spiral arms. Within this massive and intricate galaxy, the Earth and its planetary siblings are incredibly well situated, enjoying a quiet, stable, and resource-rich region of space that has allowed our civilization to thrive and look back out at the universe.